Good morning. So last day we had a couple of issues because my laptop had some issues, my internet connection had some issues, lot of things had happened. So we really, I could not really finish as per our plan. Okay. So today what I'm going to do, today actually what I'm going to do, I'm just going to see the other way of this. Just remember our discussion, and we just formulated few things. So one of these things is actually like Schottky diode Shockley model. This is Shockley model, and as per the Shockley model, we got the equation in this format, right? Just let me write. So this is the things that we have got our last day, and this is sometimes called 3 by 2 power law. Right? 3 by 2 power law. There's some modification of this rule. So one of these things, like we often write mu 3 by 2. Right? So that's what we have derived last day. And this is called, we are saying that saturation region. Okay. There's another form that we often encounter, that is actually, can you remember what is the form that we often encounter over there? That is called the Millman's law, or we often see these rules, and here everything is equal to yes, right? That we have actually derived last day. Okay. So I have the printout, so I'm just okay. Now, with all this assumption, the main assumption of this theory is that, like, you have n plus, sorry, source, you have a drain, and you have a gate, right? This is the assumption, and we took a call like this is source, this is drain, and this is void. we took a call, like if really, like if the electron try to flow over there, due to this small pinch of condition, this is the small pinch of condition. Due to this pinch of condition, you are getting a saturation current. So you are getting saturation current due to pinch off. So that was the assumption made by Shockley due to pinch off condition. You know that part quite well. We had a long discussion on this. Now there will be other way to get this saturation current, and in this case, what was the idea? Idea was like little bit different, that you have something called the L, that is channel length, and this, if this channel length is very small, so you know, if the channel length is very small, so what will happen? Your average or your electric field E, EDS by L is very high, so electric field will be very high. And once this electric field will be very high, you remember our last day discussion, you will get a saturation, because this is velocity and this is electric field. Right? You will get a saturation. So you can say it is a critical field, and above the critical field, if your E is greater than EC, above the critical field, and you see this is my saturation zone, and this zone is actually E less than EC. It's a kind of linear zone. And the thing is that if your electric field is so high, and if you are in this linear zone where velocity, this V's velocity is always constant, so you will get always a constant current, almost constant current. Remember my word, like almost. I'm not saying it is perfect constant, but almost constant current you will get. So that's very important over here, right? And that was what we had a discussion last day. Now we really need to see a modified. So we really need to see a modified IV characteristics where this modified IV characteristics where the channel length component has been included. Channel length component include, or channel length component because where channel modified where channel has been included. And how we have got it, that's what we are going to discuss today. Like previously, you see this IV characteristic, there is no component. There is no component of channel length. That you understand. There is no component of channel length. There is okay. So there is no component of channel length. So this equation is valid. That's what people are saying, that this equation may be valid for both your long channel and short channel MESFET, right? But people are saying no, it is not possible, because you know this what we have observed, this expression is good for long channel, where current saturation, where I saturation is due to, I saturation is due to what? Due to pinch off condition. Right? So that is long channel MOSFET. So that's fine. But what will happen if you really shrink down your device architecture, and then how it looks? Remember that one. So now, what is the benefit of short channel? That I am requesting you please look at, because remember this expression, like this, like a governing expression. If you see, this is actually IDA mu CW by 12. This is actually just looks like a CMOS expression only, MOSFET expression only. So whatever the benefit you are going to have to reduce the MOSFET rules, you will have same thing for MESFET. So the benefit of short channel more or less same for MESFET. Why more or less? Because remember, MESFET, there is no as such called a P-type semiconductor. P-type like P-type gallium arsenide we hardly consider, so there is no CMOS, right? But thing is that if you reduce it, so more and more number of like transistor you can incorporate if possible. Like since it is the same expression of just a single MOSFET type of MOSFET, so you get same, you might get the same benefit of the switching speed, power delay, and all these products. So how, what is the rules? What are the rules of the CMOS scaling? That you please find out. Wikipedia, nice literatures are available, or you can go for Dennard paper. So which I am going to share you. So Dennard also, if you go through the Dennard paper, you'll understand the rules of that CMOS scaling. And since it is kind of same expression that we are dealing, so hopefully this will get almost all benefits. So that's the thing. No, we need to reduce the package size. There is no, you need to reduce the size. There is no actually doubt on it. Why? Because the moment you reduce your package size or your length of your what is called your transistor, definitely you can put more number of transistor in a particular package. Another thing is, you remember this. So suppose you have a MOSFET. Suppose you have a PCB board. So you have a CMOS board, CMOS board, which is connected to your MESFET. So it can happen like MESFET and it is CMOS, right? So this is happening like in whatever MESFET output you are getting, whether it's a modulation, demodulation, whatever, it is actually processed by CMOS circuit, right? Now you know the CMOS is actually very small transistor and combined of transistor, and MESFET, suppose it is a very big. The beauty of having small CMOS in your PCB is gone, because ultimately your structure is actually very big. Suppose it's a 1 centimeter by 1 centimeter, right? So here actually you can accommodate CMOS and MESFET all together. But if your MESFET subject is very big, you are having maybe same CMOS but big, very big MESFET, which actually overall the PCB size is really high. So people don't want. So people want, since I have to integrate to the CMOS circuit. So CMOS is a very small component. So we have to reduce the MESFET also, or MESFET like device also, so that we can cook up, right? So that it should be compatible package, right? So that we can reduce the overall size of the whole PCB, So that means overall payload would be very, very low. So that is the idea. So we need to reduce the MESFET. Now, how to incorporate the contribution of what is called like a length, channel length L. So there actually, let me write. So how to do? So just do that part. We have to write the basic expression, which is G0 by. Let me write my basic expression, VDS minus VP0. Okay, let us represent it to the SAT, just the saturation voltage, because everything is happening at saturation point, right? So that's fine. So nothing is happening to the linear zone. So we are linear zone. We are actually nothing. So let us represent it to the saturation zone. You take G0 V0 common, so you will get it is the same wave actually. Now let's represent. So UGS VDS, right? So we can write. Well, doesn't mean that we have to represent, but you can represent. So this is the one of the ideas we got. Now, same thing I can tell. Now, this is the one of the ideas just modified. See, it is nothing but mathematical manipulation. Now, there are another things that I was trying to calculate another kind of current equation which is very general, right? And how we can calculate just apart from this one, how I mean another current expression. So look at that. J into A. What is J? Q N mu E mu E into A minus H. You can write X, okay, into W. So Q N mu W So I'm writing E L into Vp0. So so since I have taken L extra, let me write L. Okay. Since I am taking Vp0 extra, let me write Vp0. Okay. This is the way. This is a simple trick has been formed by the group of scientists. Okay. So they want to call it something else. I'll tell you what it is. Then you take the A 1 minus, right? Now Q n mu W by L into A, that is nothing but G0. It is nothing by Vp0. Okay. And this component they have represented, this component, whatever it is there, they have represented with a component called the alpha. Okay. So alpha into GBI minus VGS, VDSAT, VBI minus VGS. So we have done this as other thing. Right? So all are actually function of 3 by 2. So no, sorry, this is okay. So as per my so V0, Vp0 into alpha 1 minus UDS. Now this alpha is called the channel length parameter or channel parameters. And these actually dominate whether my expression is short channel or long channel. For example, for long channel, you see that EL by Vp0 is greater than 1. For short channel, it is actually EL. Now, how it is effective, I'll show you in a minute, but this is the way people are actually representing. Okay. Now, what is the value of alpha? Value of alpha, like you can identify, so you have to just you have to equate this expression. Let us write 1, and this expression, let us write 2, and that both we have to equate. So equating 1 and 2 will get like Z0 V0 help me if it is wrong. Third UPS plus UGS 3 by 2 minus UPS 3 by 2, right, is equal to the other parameter what we just now calculated, Vp0 into alpha, Vp0 into alpha 1 minus the value of alpha. So that you can find out. So this is my alpha value and it's really big value. Okay. Now the question is like how people have tackled this problem, right? So people actually, it's very difficult to tackle this problem. So what people have done, people did lot of measurements, like they are trying, they just took a lot of measurement from any of these expressions. So you can take this expression also, like for an example, like you can take this expression also. You can take this expression, okay? And what they are trying to see, that they are trying to plot theoretically, like the dependency in this manner. UDS into alpha into different VGS, UGS at different UGS. So that is they want to plot. They have plot and they have seen like this is actually numerical and they have said that it is kind of analysis or experimental data. Experimental data. So that is the dependency they got and what they are trying to see. Now, what is the best fitting? So we got a numerical from that. You understand, I hope you understand that how you do the curve fitting properly. So there is a MATLAB tools you already have. So you just take G0 value of, because you know the dimension. So you know the G0 value, the conductance. Okay. For a particular diameter, what is the VP0 that you can calculate? And then you are throwing for a constant UGS, you are throwing different value of UDS. Okay, for a particular UGS, you are throwing different value of UDS and trying to measure alpha, or vice versa. You are throwing different value of alpha and trying to measure UDS. So and vice versa, right? And that is actually called the numerical part, right? So that they have done, right? So and then they said like what is the best curve fitting for it. So what is the parameter best curve fitting? They are almost done. So what is the way that they can have a best curve fitting? So actually, so what is the value that they have to consider for UDS theoretical? So they do that part and they get a best matching of this value 1 minus UGS. Okay, alpha plus 1 minus UGS. That is what they got. Okay, and this is they consider as the experimental value. So from that they again back calculate and find out. So this is the UDS, and if this is my UDS, and that is my best fit. Okay, and that satisfies all the values of alpha, UGS, and everything. It's simple curve fitting. I know you know. So you have good. I think you have already good understanding of curve fitting. So that's fine. Then you got the UDS. So you take one of the expression. So you take one of the expression IDS. Okay, suppose so IDS you can take. You take alpha. Sorry, G0 V0. Okay. Alpha G0 V0. Okay, I'll write here actually G0 VP0 and 1 minus UDS. And here this UDS value is already there. So what you have to do, you have to just put it back this UDS value, or other way, sorry. You have to put UDS value over here. Once you put this UDS value over here, you will get a modified expression, which is your work to do it. I think you can do it. G0 VP0, just find out. It's a simple mathematical calculation. G0 5 VP0 alpha 1 plus 4 alpha 1 minus dBi. So, and if you do all the detailed calculation, it's simple, like G0 value, you have to G0, you know, Q and mu, W by L and all these things. Similarly, everything you put, so you will get a value like mu n C W by 2L 4 alpha 1 plus 4 alpha into into VGS. What is important, like earlier case, we don't have this component, but now we have modified case. This component is called, okay, and here actually this component, you can say sometimes people are saying represent it's beta, okay, beta 0 also. So this actually kind of controlling whether it is short channel or long channel. For an example, if it is a long channel, so my alpha, that is E L by Vp0 is greater than 1. Okay, in this case, so that means my alpha is greater than 1, you can write. Okay, so if alpha is greater than 1, 4 alpha by 1 plus 4 alpha, you can write 4 alpha into 4 alpha equal to 1. Right? Because alpha is very, very high. So 1 plus 4 alpha, you can recognize it is equal to 4 alpha only, and that is 1. So that means this, in this case, your IDS is exactly coming back this formula. So what is your IDS? IDS will be, you just see, IDS will be coming back mu. So IDS, actually I have to write something. IDS for long channel, you can write L is equal to mu C W by 2L VGS minus this. Exactly what we have got. Exactly what we have got. Okay. Now what will happen? IDS plus long channel is fine. So we can write case 1. What will happen case 2? Short channel device. For short channel, you see my alpha, so 4 alpha by 1 plus 4 alpha. You can see that 4 alpha by 1, so it is a 4 alpha, right? Because it's a long channel, short channel, so you can assume it, right? So short channels means, you know, alpha greater less than 1. So that's what I have written. Now in this case, what is my IDS? So IDS would be mu C W by 12 into 4 alpha into VGS minus V threshold. So in this case, you see another problem, mu C W by 2L. What is 4 into alpha? Alpha means E into L by Vp0 into VGS minus V threshold whole square. Right? So you see that L get cancelled. You see that this LL and this get cancelled. 2, you will end up with a 2. Okay, so what is your final expression? Final expression is mu C W into 2 mu C W into 2 into E Vp0 . Now look at that. This is a short channel part, and here you see the good thing, or the thing is that there is a no L, there is, it's a L independent, channel length independent. Just look at that. Because if you go to the original expression, like long channel part, you see it depends on the chain L and L. So L dependent, right? You have a long L dependent for long channel. Same for our MOSFET also. So here actually L dependent, and if it is a short channel, it is a L independent. It means what? So let me actually further modify. Here you have a mu and you have electric field. So you can write GC CW GP0. So what is my VC? Okay, I think it's better to not to write VC. Let it be here. E and me. So what I am trying to tell you that it is my V, it is my electric field. Okay, the electric field might be so high. This electric field definitely, because that is why it becomes a short channel. So this is my EC. You are in this region. Your EC means your current in this case equal IDS into short. What do you mean by this case? Like, you see, the problem is that what I am trying to tell you, like here, yeah, so this length is so small, the current is already saturated. So the moment current is releasing, the moment electron is releasing out of the source, immediately it actually experiences the huge field. The moment electron is releasing from source, immediately it is experience huge amount of field, and that is what is happening. That you are getting always a constant current. You are getting always a constant current, because the moment electron. So here actually, because your L is very small, since your L is very small, electric field is very high, and suppose it is more than EC, your electric field is very high, and suppose it is more than EC, then what will happen? Whatever electron is actually coming out from source, it immediately experiences a huge electric field, and current is more. Current is actually huge electric field, and due to the huge electric field, you are getting a constant velocity, and since you are getting a constant velocity, because current is current is always a constant, because J is equal to Q and V. So if V is a constant, so if V is constant, your current is also constant, right? Because Q and N is independent. So if V is constant, so definitely current is constant. That's what I'm saying. So you are always getting a constant current. Now the question is, people are always saying that, okay, if this is the case, like what our problem is that to get a MESFET very small. Why it is small? Why we want small? Because so that we can put into the same PCB where small component CMOS is there, so we can have a small MESFET. So it is kind of matching, right? We can reduce all the dimension of PCB, payload, as I told you, all these things. But what you are saying, that if you reduce too much the channel length, then you will get always a constant current. So it is the current, whatever you are getting, it is independent of L, right? That means there is no benefit of having high frequency. I mean to say, like, if I mean to say, if the channel varies over there, channel varies up to a certain length, below a certain length, you won't get any, you are getting always a constant current, and that means constant GM, and definitely constant frequency. So you are not getting any benefit out of that, right? Forget about, no benefit at all coming. Right? So only thing is that you might decrease the size, that's all. But are you getting any benefit of increase of frequency and all these things? No. where you are getting a frequency response or everything better in CMOS, right? So people are saying that then there is no point of having discussion on like a compound semiconductor, 3-5 semiconductor. Why? Because if it is a short channel device, you are not getting any benefit. You are not benefited. So why we are not? Why we are? Then why we discuss on it? It means that you cannot go down to a particular length. Then there is no benefit. So with this argument, approximately 7-8 years, the whole experiment, like five, no, not 5-6 years, the all compound semiconductor research was stopped. Okay. After that, there is one invention, and that is called the velocity overshoot effect. And that is dramatically changed the situation of this compound semiconductor region. The theory is called the velocity overshoot. This velocity overshoot effect, which we are going to discuss, but that actually changed all the idea of having gallium. So those people who are telling that beyond a certain, below a certain length, there is no benefit of having gallium arsenide, they actually stopped after seeing this velocity overshoot effect. You might have heard this term velocity overshoot effect by impact diode discussion somewhere. So like or GAN effect or GAN effect. I don't know whether you heard this thing, but this all actually called the velocity overshoot effect. Depends on this velocity overshoot effect, which we are going to discuss. Okay, not now, because if I take it, I have to discuss a lot of things, which I am not going to do now. But what is important? Uh, these things I'll take care tomorrow only. This is called the velocity overshoot effect and how it and the modeling part also, right? So yeah. So one thing I just trying to, I don't know whether I have. So I just try to explain. I'm trying to explain one beautiful theory. Okay. Okay, just before I come to velocity overshoot effect, which I'll take tomorrow only, because today it's not possible because tomorrow only, because there is something that needs to be discussed and which we need some more time. So there are another important part that we really need to know. You know, till now, whatever we are discussing, the MESFET, before we come to the velocity overshoot effect, we need to know little bit of some other things, other aspect of this MESFET. You know that all the high frequency devices actually made of depletion region, depletion type of MOSFET. Right? MOSFET. Okay. Which was like I was okay. So depletion type of MOSFET, you know, power hungry device because it is a I always off, always on device. Always on device and we are actually turning off. Okay. So since it is a always on, so it is a power hungry device. Now, now the question is the following. Okay, so these are the disadvantages. The question is the following. So can we have enhancement type of things? MESFET? Not MOSFET, sorry, MESFET. Can we have? So can we have an enhancement type of MESFET? Which is always off. So this is because this is very important because uh, some people they don't want always want because it's a power hungry device. Some people they want enhancement and it's a low power device. So the question is how to make ion like depletion type MOSFET uh, to a enhancement type MOSFET, which is always off. We have in just I'm giving you hints. I think you can understand if you follow the hints how to make it simple. So you know this is my metal, right? So you know this is my metal. No doubt on it, this is my metal. And suppose this is my gallium arsenide. And that we have known that this should be my gallium arsenide. And you have to, you need to have such kind of a kind of device, right? So what I'm trying to tell you need to have such kind of device. The moment you know metal, which metal you have actually this is my metal. So you know which type of metal you have used for with the gallium arsenide. So you know metal gallium arsenide, Schottky contact, right? Schottky contact. If you know these things, so you can calculate what is my VBI, right? So metal work function, if you know, and gallium arsenide, electron affinity, you know, and you can approximately calculate what is VBI, built-in potential. And if you know the VBI, so you can also find out XD, depletion width, right? So this is if you know find depletion width, then your work is that to have a thickness of gallium arsenide, which I have represented earlier A, which should be XD. So since you know the XD, so A. Remember, I have not applied any voltage across the source. I have not applied any voltage across the gate. I have not applied any voltage across the drain. What I did, I just find out what is my VBI. And since I know VBI, what I did, I just find out XD. Once I know XD, and that I put as my A, right? Then what will happen? Because this is already a built-in potential is there, and this built-in potential should lock my voltage. Hello? 7 minutes. 7 minutes. So you know the built-in potential. And due to this built-in potential, you know, so see, the moment you have, so what I'm trying to tell you, just the moment you have the structure, you already found a built-in potential, right? You already, always we are having a built-in potential, and this built-in potential, if it is sufficient, it can close your junction always, right? So earlier what will happen, like you are trying to close it. Depletion type of MOSFET by applying gate voltage. Here we are saying that my built-in potential is such that it is already closed. My A is so small, it is already closed. My doping profile of N is doping profile of gallium arsenide such that my depletion region actually closed this junction. Now in this case, you know, what is my IDS? In this case, since we have closed this junction by VBI, by gate, just find out our comment, I think 3-4 lectures before, that if you want to close your junction by gate, whatever you are applying, so there is a gate you have applied, another thing drain. So they are actually pushing and gate is trying to close it. So there will be like a tug of war is happening. Whichever is actually wins, and they because of that the current profile actually dominates. For example, like gate is trying to control and your drain to source is trying to pull. Okay, if my VDS is such a high level that it is higher than whatever the gate voltage you have applied, the electric field is such a high, whatever gate voltage you are applying, so you will get an opening. Okay, right. So here what you can see that it's already closed by my gate voltage. Now you are slowly increasing your, now you are slowly giving your voltage. But since it is a gate voltage is all, since it is closed by gate voltage, okay, so or small region of drain to source voltage, or very small or drain to source voltage, so you can see you won't get any current. Just like your everything is closed. Okay. Now, how to get a current out of that? How to get a current out of that? So it is actually simple things. So it is equal to 0. Now I try to make a current out of that. So if you want to make a current out of that, you have to open the little bit of gate voltage, right? If you want, so how to open the little bit gate voltage? You have to give VGS as forward bias. You know that part. You need to give little bit of forward bias. So forward bias, if you give, what will happen? It will open up little bit of junction. Okay. So there is a current flowing. Okay. So in this case, if you are applying source to drain voltage, you will get a current. Okay. You will get a current. You will get a current. Now drain to source voltage is such a high value is that you will get, because remember drain to source voltage you are applying as a reverse bias. So what will happen? You will get almost like the same profile and you will get a saturation current. So in this case, you see that the whole thing can be turned with a little bit of negotiation to enhancement type MOSFETs. The difference is actually simple, like begin with your built-in potential such that built-in potential are corresponding to XT, the depletion region such that it's already closed. Okay, now you try to open that, now you are trying to open the channel or open that channel region. How to open it? So you just have to apply a little bit of forward bias. Only you get a current. Then the theory is same, right? So this is the way people actually trying to make enhancement type MOSFET also, MESFET also. Okay, then there are like, I saw a lot of like in power electronics zone, they are actually saying that though it is HEMT type of device, but it is an enhancement type of MOSFET. MESFET they are using. Okay. Enhancement type, HEMT type. The idea is like, so when you see the structure or any material data sheet, don't confuse like whether it's a depletion or enhancement. So whether it's a depletion type of MESFET or enhancement type of MESFET, the philosophy is little bit changed. Okay, but the current characterization to everything is more or less same, because you can understand like even it is long channel MESFET, if you try to close this junction by drain to source voltage, you need to have a pinch off. Though it is actually kind of what is called the enhancement type MESFET. So try to look on these things. So enhancement type MESFET structure from the Wikipedia or something, Google, YouTube, just to get much more idea on it. I think that is sufficient to take it my next lecture in the velocity overshoot MESFET for both, for depletion type and enhancement type. So this enhancement type, I have not discussed anything. I just give you a clue. In fact, there is no book which actually discuss everything, but I think this is clue is actually sufficient for you. What you have to do, okay, current voltage characteristics also is the same. It is also following the same rules of alpha and everything. Only thing, the threshold voltage value will totally change. Only thing is that the threshold value voltage is totally changed. Okay, the enhancement type of MOSFET, the threshold voltage value is changed. For our case, so My question is, what is the threshold voltage for enhanced base type MOSFETs? That you please try to find out whether it's the same or it's a little bit different and everything. So that you just try you to just think about. That's all. Okay. So I'm stopping over here. Please let me know if you need any clarification. Hello? Hello?
No, sir.
Okay, thank you.